Welcome to Geology Basics video mini lecture number 5, our last of our 3 videos focusing on the process of science. In this one, we're focusing on what are scientific hypotheses and theories. This tutorial focuses on the scientific meaning of theory, hypothesis, and observations and how they're interrelated. When scientists are doing science, we really don't worry much about terms like hypothesis or theory, but it's important for everyone to know that the meaning of these terms in science is different than sort of everyday definitions. So take a minute and think of everyday definitions or any definitions you've heard of theory or hypothesis. Is one of these two terms more general, one more specific? What do you think? Let's start with hypothesis. In science, a hypothesis is an explanation for how something specific in nature works, or it can be an answer to a specific scientific question. A key aspect to a hypothesis is that it must be testable using evidence. Here's an example of a hypothesis. A scientist observes the appearance of 3 different species of butterflies. The one highest up in the mountains is in the alpine zone. The scientists noticed that the alpine butterfly species has characteristics kind of in between, but like both of the other 2 lower elevation dwelling butterfly species. So that would be an observation. Scientists are often very curious people, and the scientist proposes an explanation for this observation based on her prior experience, background knowledge, observations, and logic. Her explanation is that the alpine species is a hybrid between the 2 other species. Theories are different than hypotheses and much more general. The scientist noticed that the alpine butterfly is darker in color, and she also knows that darker colors absorb more light and heat from the sun, so this could impact body temperature. That means that the darker color could be an advantage to the butterfly at the alpine elevations for its survival. In this explanation, she mentions natural selection, which is a theory, which is a broad explanation for a wide range of observable phenomena. It is short. That is, it's concise, it makes sense internally, it makes predictions, and is broadly applicable. So it's important to know that neither theory nor hypothesis are hunches or guesses or educated guesses. They're very well-reasoned, well-educated sort of ideas and explanations, theory being a larger and more general kind of explanation than a hypothesis. In science, a theory fits 3 criteria. It has to be exceptionally well supported, it has to be a broad explanation, and it has to be about how nature works. Theories take a long time to develop, and they need to be supported over and over through the process of science. For a theory to be accepted, there can be no findings that directly contradict it. Finally, theories are broad explanations of how the natural world works. We're now going to look at the connections between observations, scientific questions, hypotheses that offer explanations for those questions, and then how a theory can be supported by multiple hypotheses. This time it's related to geology, and in fact the development of the theory of plate tectonics. We're starting with 2 observations. First, geologists found many cases of fossils of the exact same species and age in both Africa and South America. The scientific question generated from this observation is, why are these fossils of animals and plants, which can't swim across the ocean that separates these continents today, found in these widely separated areas? Geologists came up with many hypotheses that could be potential answers and explanations to this question, and 2 main ones emerged. Those fossil animals and plants could have migrated slowly across land bridges that aren't there anymore, or the continents were once together but have since moved. Land bridges between continents do happen. Think of North and South America, now connected, and we know a lot of different types of evidence that North America and Asia were once connected across the Bering Land Bridge during times of lower sea level when glaciers took in a lot of the world's water. But despite a lot of looking, there's never been any evidence discovered of a land bridge between Africa and South America. So geologists reconsidered alternate hypotheses, including the idea that continents could have moved. Completely independently from the idea or the observation of the fossils, geologists also found evidence of very large continental glaciers on several continents in locations that are now really close to the equator, so in the tropics. Continental glaciers like those on Greenland and Antarctica today do not generally form far from the poles. So the question that emerged was, how could glaciers exist in these tropical locations? Many hypotheses were generated. Two examples are given here. One, perhaps the entire planet was cooler and glaciers could form in tropical areas in those times. Or maybe two, continents with glaciers were once joined together more towards the poles than they are today, but have since moved apart and towards the equator. The hypothesis suggesting that the entire Earth was cooler was ultimately rejected by scientists because rocks of the same age in different locations contain evidence of tropical plants, including large deposits of coal that can only form with such plants. Once again, the hypothesis suggesting that moving continents could explain observations was considered more likely. A really important part of science is that scientists change their minds when evidence points them away from their original ideas. We almost never get it right the first time, but instead learn a ton from testing our ideas and then testing more. These hypotheses are only two examples of many more that attempted to explain multiple different types of geological observations that could all be explained if the continents moved. But this was considered a radical idea at the time. We're talking back a ways in time. So in this particular case, we're basically talking about 1890s to about 1910s. This was still considered radical when one scientist proposed a larger theory called continental drift. You've probably heard of it. Sometimes it's equated being the same thing as plate tectonics, but it is not. Continental drift theory stated that Earth's continents move slowly over time, plowing through the rock that forms the ocean floors. At this time, no one knew much about the ocean floor except its composition, what rocks it's made up of, or what chemistry it is. Continental drift theory supplied a prediction that the rocks making up continents should be strong enough to move through oceanic lithosphere as the continents move, like a ship in the ocean moving through water. This prediction led to laboratory experiments on rocks, and both experiments and eventually early computer models in, say, the 1950s and 60s demonstrated that continental rocks were not strong enough to plow through oceanic rocks. These observations directly contradicted the mechanism of continental drift theory, and so it was not accepted by the scientific community. Again, scientists changed their minds in light of new information. Over the next 60 years, new technologies uncovered more and more about the ocean floor or the oceanic crust and features on the ocean floor. Many new observations were made that generated new scientific questions and new hypotheses, and finally the larger and more general theory of plate tectonics was developed. Now that you have an idea of how this sort of diagram works, we've got three empty boxes. So, where should hypotheses go, and where should a theory go? If you said the hypotheses should go in the two green boxes on the left side, you'd be right. And this diagram illustrates the fact that multiple hypotheses support a single proposed theory. That's the green box on the middle. The observation that the youngest rock making up the ocean floor is in the middle of oceans is explained by the hypothesis stating that new ocean floor forms in the middle of an ocean because this is where oceanic crust splits apart and new crust forms in the middle. Sometimes this is called the seafloor spreading hypothesis. The observation that deep earthquakes occur near oceanic trenches is explained by the hypothesis that oceanic lithosphere bends, sinks, and subducts beneath continental lithosphere at subduction zones. Both of these hypotheses support the larger theory of plate tectonics that developed from these and many more sets of observations, scientific questions, and hypotheses. The proposed theory of plate tectonics states that the lithosphere is the unit that moves, not continents like proposed by continental drift. The lithosphere is divided into plates, and in some places oceanic lithosphere forms, other places it sinks below other pieces of lithosphere and is destroyed, and that the continents move as part of these lithospheric plates. They're carried along with them. The theory of plate tectonics makes many predictions, one of which is that Africa and South America are currently moving away from each other, which has been confirmed by many lines of evidence, including direct GPS measurements of plates moving. Before you go, please think about those last 3 learning goals, and specifically about differences between theories, hypotheses, observations, and scientific questions. The story told here about plate tectonic theory is one example you can use to answer these learning goals.